Hi, thanks for watching our senior design presentation. We're Team 7, and our project is the Poor Man's Logic Analyzer. I'm Spencer, this is Abdalmajeed, and this is Robin. You may be wondering what a logic analyzer is. It's an electronic instrument used to measure the signals inside of a digital circuit, and is most commonly used for debug purposes.
Our project is sponsored by Cyber Semiconductor, and our mentor is Steve Dance, software engineering. They are providing us with a PSOC 5, a programmable system on the chip. It's a new development platform that combines analog and digital precision with a high-performance 32-bit ARMS MCU.
This will be a standalone logic analyzer centered around the PSOC 5 that will interface with the host PC over USB. We'll be designing the entire system, including the analog probes, the digital circuitry, the firmware on the PSOC, and the PC software that will display the signals. Our logic analyzer will be inexpensive and portable. It will be designed in mind of freshmen in ECE who can use this throughout their college careers for debug purposes. It should be in the price range of around a textbook.
Right, let's talk about engineering requirements right now. For example, our first one, the ability to monitor 8 channels. It's pretty self-explanatory. It means there will be 8 input probes for independent channels and signals. It will also be able to analyze 10 megahertz signals on each of these channels, and that means the PC will accurately display the 10 megahertz waveform. It will also be a USB-based device that is powered by USB, and its physical connection back to the computer will be USB.
We're going to use Cyber's PSOC 5, which is required by our mentor. We're going to be reading logic between 5 and 1.8 volts. So the user will be able to choose between 5, 3.3 and 1.8 volts.
Alright, and some other engineering requirements will be the PC will be able to display the digital signal waveforms, and the PC will be able to decode basic protocols, for example, USAR.
And now we have our top level block diagram. On the top we have our environmental, which is standard indoor conditions, dry conditions, and a moderate G-force drop of about 2 Gs. You have our user inputs that come from the GUI. That includes what channels they want to read and how they want to trigger on them. We have our input probes, which are the physical probes you would hook to your digital circuit. We have USB power, which is the 5-volt power that comes with USB that will be powering our logic analyzer. On the output, we have our waveform. That's the GUI waveform a user can interact with to help debug their system. The status lights are LEDs. We have 3 of those. The first one is the power one to indicate it's on. The second one is the one that's when it's waiting to trigger, and the third one means it's triggered and it's currently reading and outputting to the PC. We have the data file. Those are savable and preloadable, and that way a user can go back through and look at all their old signals. Output probes is like the output control. If a user wants to change a 1 and 0 on their test system to help debug, they can do that. And the USB connector is the physical USB connection from our Poor Man Logic Analyzer box back to our host PC.
Now we'll be covering the block diagram. I will be discussing the PC blocks, which are inside the red box. Here we have 4 blocks: the user GUI, the serial driver, the protocol analysis, and the software code. The software code will be written in C#. The GUI is what the user will see and where they can input settings like how many samples to take. This is also where the waveforms will be displayed. The users will be able to save data waveforms and also be able to open previous data waveforms. The serial driver is the software portion that communicates with the PSOC over USB. The protocol analysis will decode our data protocols, which will be in USAR.
Hi, this is Spencer Leuenberger, and I'm
I'm going to be talking about what's inside the green box on your screen right now. And at the heart of it is the PSOC 5 inside the logic analyzer. Starting off at the top is the firmware code. This is just the programming and embedded C that goes into the PSOC 5 USB UART and the PSOC 5 MCU. The MCU is in charge of basic input and output. It reads the input signals, gathers that data, and sends it to the USB UART section. It also takes data from the PC, transfers it through USB out, and turns that into status control and output control signals. The USB UART is a physical implementation over USB that is actually a serial port, and it's also in charge of encoding the data coming from the PSOC 5 and compressing it out so throughput can be met.
Hey, this is Majid. I'm going to talk about the blue box. In the power plug, we have a 5 DC voltage coming from the USB, and it will be regulated into 1.8, 3.3, 5 DC voltage. In the output control block, we will be controlling our output voltage by the MCU. In the LED status plug, we will turn on and off our LEDs by the MCU, and it will show different light colors for reading, waiting, and power. The Pro plug will show the physical connection. The purpose of protection plug to not allow more than 5 DC voltage to go into our PSOC and destroy it.
Here's an example of the reading and waiting circuit. It will run under the example mode. The reading and waiting circuit. We're gonna use the HLMP. It will run under the reason for that, it's well known for high efficiency and low power consumption. The reason for that, 5 volts will known for high efficiency and low power under the cutoff mode, so no current is gonna flow through our transistor. When it's 0 under the cutoff mode, the current is gonna flow through it and hit the LED and turn it on. 0. The current is going to flow through it and hit the LED and turn it on. We didn't really need the R2 to build our transistor, but we still needed to limit the current and get the amount of current we needed, which is 2 milliamp. That gives us a consistent light.
Alright, now I'm going to delve into the firmware part of our top level block diagram. And this is a screenshot from the PSOC 5 creator from Cypress. It lets you design and implement all the internal circuitry that things relate to each other. And actually there's no internal circuitry, we just have output circuitry, which we have our output pins, our input pins, and our USB UART. The real money part of this is the input signals, which are mapped to special input-output pins, and they let you reference inputs at a bunch of different voltages, and that's how we're going to be able to get our 1.8 volt, our 3.3 volt, and our 5 volt. And over here we have our LED control output, our output level select, and our output enable. Next slide. And this is a screenshot from the design-wide resources, and this helps you label your input and output pins. For example, I've mapped the special input-output pins to these pins, these pins, these pins, and these pins. And those are chosen their specific inputs on the PSOC 5 package.
Alright, here is our PC state diagram. We start with opening the software, which then displays the GUI and waits for the user to input. When the logic analyzer is connected, which is over here, it now allows the user to input settings and then displays that the logic analyzer is connected. And once it is connected and a user inputs a setting, it then sends it to the logic analyzer and goes back to waiting. And when our start button is hit, it sends start to logic analyzer, then it waits for data to be sent to it. And when data is received, displays the waveform, then goes back to waiting. And then once the user hits the stop button, sends stop to logic analyzer and goes back to waiting. Next slide. Here's a basic rough draft of what our GUI may look like. It has 3 sections. One for user settings to be inputted, measurements, and displaying of the waveform with each channel. And here we have buttons for triggering.
So for the fall term and the winter break, we're going to finalize our design spec. So for the winter term, we're going to finish prototyping and bring all our system all together.
And in spring term, we will finish bringing all our systems together and add any extra features if we have time. And then we will be getting ready for the Engineering Expo. And thanks for watching.